lecture because the thesis resolvent is defined as a difference of two. So, and why I'm so picky, because tomorrow for me the sign will be quite crucial to some extent, and actually it shows that although there are these two cuts, only one of them somehow represents some physical positions of the roots, and that's why it's integral which counts the number of roots inside is positive. Another one is like an effective cut, which actually contains negative number of roots in some sense, and that's just due to this technical reason, the way that resolvent was defined with this minus. So only one of these cuts is somehow physical, and another one is like an image of another group of the cuts. Just in this PMU system, these two cuts, they will play a different role. So there is no complete symmetry. So today is the toughest day. So the first lecture, I will try to derive the PMU system. And for that we will have to go through some rather painful steps, because on the way to the beautiful underlying structure there is the ugly TBA equation. We saw some examples of TBA yesterday for the spin chains, and already even for SU2 it was rather complicated. And here it's even more complicated because we have to consider an extended symmetry with high rank. And so let me start by first writing SU2,2/4 spin chain Bethe equations. So in order to write down the spin chain, the Bethe ansatz of the spin chain, it's useful to first make a picture of the corresponding linking diagram. So and we, to each node of this linking diagram, so you see it's roughly like SU8 linking diagram, right? So with 7 nodes, but some of them are fermionic, and that's because we have like 4 fermions and photons in the fundamental. And then the prescription is the following. So if you want to write a spin chain a Bethe ansatz equation for no matter which linking diagram, what you have to do, you have to introduce a type of beta roots for each of these nodes. So it's a U1, K for those, U2, U3, A and U4, and I hope you can continue this lower part of this diagram yourself. An exercise. So the next step is to write down the Cartan matrix. So Cartan matrix for the super stuff, so let's denote it by K or by C. So it is a 7 by 7 matrix which just encodes this information written here in the diagrammatic form. So first it starts from a fermion. So, and Cartan matrix, what is Cartan matrix? Is a collection of scalar products. Right? Basically, so fermion with fermion scalar product is 0, right? Because fermions, they hate each other. And like in the bosonic case, here it is 1, then it's 0. Then for the next line, we have just the usual SU2 node. So it's -1, 2, -1. So then again we have fermionic nodes, so on the diagonal I should put 0. But then what happens at each fermionic root is that the sign changes, so from -1 to 1. And then instead of 2 for this middle node, we get -2, 1, 1, and so on. So that's how the Kaplan matrix looks for this diagram. So that's just the usual SU2, and this is like minus usual SU2 because we cross one Fermi. Each time we cross one Fermi, we flip the sign in this elements of the Kaplan matrix. So now, why do we need these numbers? As we saw yesterday, they actually appear in the Bethe ansatz as a coefficients in front of i's, or rather i's over 2. And then we have lots of products of the roots, and so it's nice to introduce some polynomials, called Baxter polynomial, for each type of the roots. So I have n a roots, and I compute product over all of them, a I minus u minus u a I. Yeah, so just otherwise I have to write too many formulas. So now what we do, we write 1 equals to, and then I look here, so it is 1, 2, 1, 2. So what appears for the line 1 is Q2. So I write Q2 with a shift minus. So in minus it means, like in the lecture before, that I shift this u by minus I over 2, and then I divide by. So the next equation, so there is some subtlety that for fermions it's +1 in the left-hand side, and for bosons it's -1. Again, I just look at this line, and what I see is Q1, Q2, and Q3 should appear. The numerator, Q1, Q2, Q3, and the same denominator. And then the shifts, they're written here. So it's +2. So +2, let me denote by ++, means twice the universal. Minus, minus, plus, minus, minus, plus. And then, so it's not very Euclidean geometry here. And do just the next line, for example. So we see that for the next line, what appears is Q2 and Q4. Q2 and with different signs. Q4 plus or Q minus, Q4 minus. So and then, so this is the ratio of two polynomials, right? And Bethe ansatz equation is just some constant equals 1 normally. So I have to evaluate this at each of the roots of the type 1. This has to be evaluated at the root of the type 2, and this to be evaluated at the root of the type 3.
Sorry, in the third equation should be Q3 minus 2.
So let's see, 3, so it's 2, 3, and 4. In the second or in this round, so it's fine. So that's the situation for the usual spin chain, right? And now I want to extend this equation to the actually the string in the ADS5 versus 5 background. So it still has the same symmetry, right? So the change shouldn't be too big. But you see these equations, they contain no information about the coupling, right? So there is no top coupling, no G, nothing. So the way it appears through the so-called constant variable. So one has to introduce this function x of u. So let's, for a while, discuss its properties. So if someone actually is capable of solving this equation, so of course, quadratic equation, so not recommended to do without Mathematica, but some people still remember the rules. Okay, so again, you're very welcome to check it because some of this could be wrong. Yeah, that's good actually. So we define this function f of u, x of u, right? But immediately we see that it's not a single valued function. It has a square root, and square root is like the most complicated function in theoretical physics because you never can be sure about its sign. Especially if it appears in the numerator. So we have to specify the cuts, otherwise we know nothing about this function. And the way we have to choose these cuts, the lecture will be in this way. So you see there are branch points at 2G, and G is related to the coupling. So this is, together with this picture, this uniquely defines as x of u, and also at the upper part, x of u, absolute value bigger than 1, to be more precise. Because if you flip the sign of this square root, that's the same. And let me define this x tilde function, that's x with square root going to minus square root, and that's actually the same as 1 over x. So if you flip the sign, that's quite surprising that it's the same as I'm just flipping. And it's obvious that this quadratic equation has two roots, x, and it's 1 over the roots of x, and not this 1 over x. So, okay, this function is something we need. And now, in analogy with this function q, which was a polynomial, let me define so-called Zhukovsky polynomial in the following way. So it's a product of x minus x of u minus x of u for a from 1 to n4, and also function b where x is flipped. So you see that actually, using my notations, I can say that b is r tilde. Alright, this is one thing. And another thing is actually easy to check, that if I multiply these two functions, b times r, and then rearrange this part up to some constant, I actually get q4 of u. Okay, so now it's easy to extend these equations for the n equals 4 superangles at an arbitrary coupling. One thing to mention is that x of u for imaginary part of u bigger than 0 becomes just q over g, and g goes to 0. So essentially this is to say that when g goes to 0, x is the same as u. So then particularly b becomes just q, and r becomes just a q, and b becomes just a constant when g goes to 0. So it means that I can, without much of harm, just add here b over b. Yes, that would look. Superscript q plus minus plus minus plus. plus or Q minus. Right, and that recoupling, this would in principle disappear. And also I have to add, to convert this Q4 into R. Okay, and after that, it extends to any coupling, and this is the by the Nordita equations for n equals 4. Of course, I mean, it was lucky that I stopped at node 3, because at node 4 it's a real disaster change, because there is a dragging phase appearing, and that's the function you don't really want to see. Stop even to black forces. But concerning these three nodes, the modification is very simple. You just add some B, which vanishes at recoupling, and you're back to the usual spin chain, and you convert some of the skews to R. Okay, any questions? Yeah?
What is the meaning of these modifications from the point of view of the ansatz?
What do you mean? That's what it means.
What does it mean if we multiply the equations by some functions? R and B.
So I mean, just replace one equation by another. It's a new equation. Now it's now we introduce this parameter G into the system of equations. Now, when you solve this equation, you find the beta rules. There will be some non-trivial functions of the coupling.
And do you correspond to some spin chain some Hamiltonian or not?
That's a good question. So actually, Hamiltonian is not really known. So it's only known up to, I think, maximum 2 loops in some particular situation. But in principle, the Hamiltonian is a mysterious thing. More questions? Yeah, but nevertheless, people managed to find the beta ansatz, even though Hamiltonian is not known. Because what they did, they used the symmetry to restrict the possible structure in the S matrix, and then once you know the S matrix, you can diagonalize, and you get some set of equations, but you don't know which Hamiltonian you actually diagonalize. So in any case, so that's the modification. So and the reason is why I write it is because I want to show you some parts of the TBA. And yesterday I argued that TBA should arrange into this T-hook just because of the symmetry. Where each of these nodes, so those nodes which are slightly away from the border, they correspond to some y functions. And we remember that y function is related to a density in the thermodynamic limit of some bound state. So let me just briefly tell which bound state which y function corresponds to. So for example, this line, so this particular point it corresponds just to a single U4, right? U4 which is real. Then this one corresponds to the string of U4s of the length 2. This is the string of the length 3, and so on. So whereas these two nodes they correspond just to the two fermions U3 and U4, and actually it's nice to just write on top the Lincoln diagram. To make it super clear. So meaning of, a bit a mess, but the meaning of this is the following, that actually this y function sitting here, it corresponds just to a single u1. And of course fermions, they can't form bound states, right, because they said they hate each other, right? They don't interact with each other, so they can't form a bound state without the help of some bosons. So that's why there is only one node corresponding to u1, which is a fermion. And this one corresponds to u3, and so this is 5, and this is 7. Okay, and then these are some bound states of u2s, and this is something complicated which involves both fermions and bosons. But that's not important. So is it clear? So remember in yesterday's derivation, y function corresponded to some bound states, and then what are the bound states? These are beta roots separated by I. So this particular node, they correspond to u4s separated by I, and these are just single fermions. So let me introduce some system of coordinates here. So this is S, this is A. So our fermions and y22, these are u3 and u1.
Why do you think the diagram makes zero?
Well, because you know the super diagrams always like to form because there are different gradients you can introduce. And so if you, this is I think an SU2 gradient, if you change the gradient then it will form another place. So it's not unique beta ansatz you can write, so for some other beta ansatz it will go like this. Okay, so now I want to actually, this information should be enough for us to try to reconstruct the debye equation for say y11. So for that, as you remember, we just have to take log the derivative of the corresponding S matrix and integrate it with log of 1 y10. So it will be fermion, something else. So what appears here is interaction. So we just, this will play the role of S. And there are actually two S matrices, one corresponding to the scattering against U2, and another corresponding to the scattering against U4. So I can write here terms I U log P plus over minus log 1 plus. And U4, as I said, corresponds to this node, which is easy to check. This is y10, right? So this is 0, 0. This will be y10. And plus minus over plus plus some other y, and doesn't matter. So the y which corresponds to u2. Right? And then if I take y22, actually we see that everything is exactly the same except that B is replaced by R. Right? So all these terms in the B ansatz are the same, and this is those, yeah.
What was the exact motivation for making this replacement and not some other way?
Motivation, of course, comes from this centrally extended SU2/2, right? So you should really write this matrix which has this invariance, which is is the symmetry of the vacuum after light point gauge fixing. And then you diagonalize the stress matrix, and that's what you will find. I'm just telling you the result and arguing why it's natural, why it's naturally connected with just the spin changes can be easy to reconstruct. Okay, so I just want to show you the simplest equations on the market, and you see already that quite complicated. Alright, so the only replacement, I replaced B by R for this equation. Okay. So now, so this is quite complicated, but let's take a sum of those equations. Yeah, so actually, both sides. So the reason is you see that actually here is minus plus and here is plus minus, so the sign should be different. So the slope then becomes just minus I slope of R plus R minus over plus. And then slope 1 plus. So another ingredient here is that, as I said, this U4s, they can form bound states. So actually, I have to sum over all the bound states, and then I will have some extra sum, which will describe me the scattering with the bound states. So in principle, it's a sum within so many terms. So that's the simplest, really the simplest equation out of all TB equations. And we will now try to see how this equation can be rewritten in terms of some discontinuity equation. So it happens that it is equivalent to just saying that y11, y22 times plus y a0 minus a is analytic for bigger than 0. So let me just give you some example. minus I over 2 d. So there are always some integrable function. So this definition works nicely when imaginary part of u is smaller than 1/2. Right? And so why do I use this example? Because this kernel on the right hand side is actually very similar to this right hand side here. So, however, when I try to deform u above I over 2, what happens is that at some point I keep this pole at the I over 2. And then my integration contour should go slightly below in order to get an analytic continuation of g of u. So in other words, g for imaginary part of u bigger than 1/2, I should use a different definition because you see this definition is problematic exactly when imaginary part becomes I over 2 because this integral diverges. And then above, if I continue above, then instead of this integral, I should add an extra term. Then this will describe the true analytic continuation above this point I over 2. So and then if I form the following combination g minus 2 pi I rho, then it will be given by this integral again. And you see now the right hand side is absolutely convergent for any u above. So this right hand side is analytic. Right? It can't have any singularities, it can't have any type of divergence above imaginary part u above 1/2. So in other words, whereas rho is an arbitrary function in principle, it could have some square roots, some crazy essential singularities, and g as well. It means that g above I over 2 could be a very complicated function. However, this combination is analytic above the real length. So similar thing happens here. So if I combine, so role of rho is played by the slope of 1 plus y and 0. So if I combine it with left hand side, then the resulting function becomes analytic in the imaginary part bigger than 0. And then you can actually revert this logic, assuming that this is analytic, you can derive this equation back. So that you have one thing which confused me, makes me slow, that there is an additional condition which tells us so these two conditions are equivalent to this equation. Okay. So the main message, actually I have this one. The main message here is that instead of writing integral equations, I can collect completely the information about this complicated integration kernels appearing from the Bethe ansatz. I can collect all this information into a very simple discontinuity relation. So telling that certain combinations of y are analytic in the upper half plane, and that so some y's they flip when I go through some cuts. When should I stop? Fine. I was so worried. So actually, so is it clear what I said? Because I thought I had no time, so I was not explaining properly. Good? Yes?
in the equations for logarithm of y11, y22 should b and r be swapped or not? Because you said that the y11 corresponds to u3. And so if you look at the equation, there is r instead of b.
No. So y1, yes, you're right. Yeah. That's good. Fine. Okay. So now, let me argue that actually this discontinuity relation, here there is a product over all bound states, that this discontinuity relation which tells us that this product is analytic. So still it's a quite complicated statement because it's like involve infinite products and so on. But let's actually see what it means in terms of T's. Let me fix one extra problem. Actually, one over. Right, so sine everything before. Right, problem. So in terms of T's, we'll see that actually it has a very nice interpretation. So first let me remind that how we go from y to t. So schematically, one can write it in this way. In other words, if I'm at some point of the diagram, say y11, it will be given by 1 to 2, it will be given by t to 3 times t to 1 over t3 2 over t 1 3. Okay. Let me write this. So y11, y22 can be expressed as so t1 2 t10 over t21 t01 is the first y, and the second y t23 t21 over t32 t12. So we see that actually something cancels. We get this combination of t's. That's for this part. Now what about this part? So let's first start from y a0. Let's prepare this object. So this is 1 plus y t1 ta minus 1 over ta plus 1 1 ta minus 1 1. So that looks very promising. However, if we bring this to the common denominator, you'll recognize that in the numerator there is the right-hand side of the Hirota equation. Right? So remember that T is a satisfying Hirota equation, and actually this can be written again as a product of four, sort of like cross ratio of four terms. Okay, so sorry, that's the toughest part. So now I want to say that in this infinite product there will be some nice cancellations again, like here we had some cross cancellation. Again, if we now write 1 0 plus, times 1 minus 3, 0 with 3 minus. Okay, number of minuses. Yeah. With 2 minuses, right? Because A becomes sorry, let me fix some typo. After 1. So it's actually 1 minus y. No. So let's just take 2 terms, right? And then more. So the first term, so it is t 1 0 without plus now, t 1 0 with extra minus, t 2 0 with minus, and t 0 0 with minus. Now the next term, I just use this with a plus 2 and 2 minuses. It will become t minus 2 0, t 2 0 with 3 minuses, or t 3 0 2 minuses, t 1 0 2 minus. And so we see indeed that there is this nice cancellation. And actually, all these terms, they will be cancelled if you do this infinite product. So this just becomes t 1 0 over t 0 0 minus. And this to be, so I have to divide this product by this result. So our function f, this combination f, simply becomes, so what's left is t1, no, t1 0, okay, slowly, t0 1, equals t3 2, that comes from y1 1 y2 2, and the rest gives no, so t1 minus and t1. This cancels. See, actually, the statement is it tells us that this combination is analytic. So just start seeing that actually the TBA equations, they are reduced into some very simple statements of analyticity of some combinations of t. Okay, but let me mention some points. That first, you see, there will be some boundary term, let's say, in this infinite product, right? And we actually ignored it completely. And that's possible, actually, that's safe to do, provided this boundary term is analytic itself. And actually, we can always do this because A0 is just a consequence of TB equations, is analytic inside the strip, d mod u smaller than a equals to. And so it means that I always can choose t's in such a way that t a0, for example, is analytic. In a slightly bigger strip a plus 1 over 2. Right? So of course, I mean, if ta0 is analytic in the strip, then if we use one of this equation, you can see that y will be automatically analytic in the slightly smaller strip because I shift the argument of u, or I shift a little bit. But that's why I need a bit of extra analyticity in t. So provided t is chosen in this way, that's fine, and I can drop this boundary term at the same time. And why actually I can do this choice? Because there is still some freedom. For example, if I change t, so as I told you, that t is analog of vector potential in the Maxwell theory, and there is also an analog of gauge transformation. So gauge transformation is generated by this function f, and the one s and 1 of minus a plus t a s. So if I do this transformation, because t appears only in these cross ratios, it will not change twice. Exactly like in electromagnetic. So I'm just telling that it's possible to choose f in such way. But now let's see actually what the statement tells us. So we have this f, and this f itself is not gauge invalid. That's because we actually dropped this boundary term. Initially it was a combination of points, which was gauge invariant, but now it's not. So, and I claim that it transforms under this f in the following way. So let me leave it as an exercise. So it transforms not only with respect to the holomorphic part of the information. So in other words, I still have this freedom, and B transforms in this way, and still this should be analytic. So now I want to say the following. So if I denote this by f, and f transforms non-trivially, let me choose such f that this f becomes 1. It's easy to see that actually I can just formally say that f is equal to some infinite product. So formal solution is easy to build because it's a first order finite difference equation. Right, so I want to set this to 1, so I can express f minus in terms of f plus, in terms of some x, and then I can continue this in the chain and somehow integrate in the discrete way this identity to infinity. So in other words, if you just formally take f to be, or b is actually f, to be of this form, then it will gauge this relation to identity. That's the property of f. So this becomes 1. So there exists such a gauge transformation which sets this to 1. But important point is that this gauge transformation also doesn't spoil the analyticity of t. Because this f is built out of this capital F, which initially was analytic in the upper half plane, so this small f is also analytic in the upper half plane. And that means that after this gauge transformation, t still has this nice property of analyticity in this. So without restricting generality, in other words, we can from the very beginning set this combination of t's to 1. So in other words, there exists such nice gauge where t, this combination of t's is 1. So in some nice gauge, which is the most natural, this t is 1. This combination of t's is 1. And now once it is 1, it must be 1 everywhere in the complex plane. And also its complex conjugate should be equal to 1. So we have two identities. In this nice gauge, is really the best gauge possible, this combination, and furthermore, its complex conjugate is 1. So, yeah, so if we divide one by another, sorry, this was cancelled. No. Okay. So what follows is that t 0, 0 minus equals to t 0, 0 plus, or in other words, we have a nice consequence that in this particular gauge t naught is periodic. That's a periodic function, and it actually constitutes a part of the spin system. It is denoted by mu 1, 2. Also, it's possible to show that just using Hirota equation. Sorry. So we are now here. So that's t0, 0, that's t0, 1, and actually we assume that's right wing is equal to the left wing. So we can write Hirota equation at 0, 0. Get t0, 0 plus, t0, 0 minus equals to t0, 1 squared plus 0. Just because there is no t here. So I can go down, so it's very simple. And actually it means that t0, 1 equals to t0, 0 plus. Of course, I have to choose some sign. So and then that we use Hirota equation. We also can deduce that t23 equals to t32. So what's the meaning of this? And actually, again, it's a very nice thing because it tells that t's living here are equal to each other. And that's what's expected from the group theoretical point of view, because, as I told yesterday, these representations, they're actually equivalent representations. So the characters corresponding to these Young diagrams would be also equal. So this is just group theoretical requirement, we can say. And the only new thing is that t naught is a periodic function. Okay, so that's what we managed to subtract from the simplest possible TBA equation. So in terms of t functions, to summarize, that's a very simple statement that there exists such gauge where t23 is equal to t32, and at the same time, this t is living on this horizontal line. They're all periodic functions, which can be expressed in terms of t naught. And so, if I now apply the same procedure to all equations, then I get very simple consequences, which are the following. First, that is TA1, T A minus 1, 0, the analytic or mu more than A over 2. That's what we discussed already. Then, in other consequences, T23 is T32 and T00 is periodic. We denoted by mu. That's what we already know, and all the information others, TB equations can be summarized in the following way: that if we now introduce this T empty, which is very simple transformation, that's given in terms of this mu. And T. So this is just the gauge transformation which says T0 as B1. So then for this T, some miracle happens, namely that T1s, so which in principle would have infinitely many cuts on this side. The Zhukovsky cuts all over the place in the complex plane, starting from IF over 2. So that's what we would naively think from the equation, but as a consequence of the discontinuity relation, what we find that if we go under the first cut, then all these cuts above, they disappear. So on the next sheet, there are no cuts. We go up, and also if we go down. So in other words, we can say that if we just decide instead of the long cut that we initially have chosen for the heat ansatz equation, take this small cut, then there will be only two cuts. So it's like a huge simplification of analytical property. Instead of having infinitely many cuts, all the equations want to tell us is that actually don't take long cuts, take the short cuts, and then this structure is much simpler.
What happens if you cross the cut at the second sheet?
Which you mean this cut?
Yes.
So that's a quadratic cut, so if you cross it, then you appear back. That means you go twice, so you appear back on the sheet. So you will again find infinitely many cuts. But if you don't cross it, you stay on the nice sheet, then you see only two nice cuts. So and that's completely equivalent to this horrible system of TB equations, out of which I just have written you really the two simplest equations. So all the information stored in the TBA can be recast into this natural requirements for T23 to be equal to T32, which is in principle a consequence which you can speculate of the group theory, and also this miraculous property of T. That's for S equal to 1. So now, just the last statement to show you how P is appearing. Yeah, and of course we should add to the Hirota equation. So now you see this T, it has only two cuts, so all T is here, it only has two cuts. And those two cuts, they move with S, so they become, this gap increases. And so actually, it's natural to assume that there are some more elementary objects which describe these cuts separately. And indeed, one can prove that in general this Hirota equation can be reduced just to two, can be solved in terms of two functions. In this way, where each of these p's has only one cut as a function of mu on the real axis, from minus 2g to plus 2g. So in other words, by introducing this P1 and P2, we immediately take into account this property, and also we solve part of Hirota equation in the right wing. So all equations here are now solved. All the information contained in this y functions and TBA for this y's is contained now in this simple statement that there are two p's which are not so far arbitrary, which has only one cut, the only requirement. So otherwise P1 and P2 are arbitrary. However, we still have this requirement that T is in this domain should have some analyticity. And this constrains us the possible choice of P's, of P1 and P2, which are so far an arbitrary functions with one cut. So now I don't have time to explain, but let me just do the statement that first any T can be expressed in terms of mu 1, 2, P1 and P2. So because now we know all T functions in the right wing and the left wing, furthermore we know that this T is the same as this one. So now using Hirota equation we can actually find recursively all the T functions in terms of those we already know. And then if we require analyticity, say of T to 1, that it's discontinuity at the real axis of 0, what we find is that mu1 2 tilde minus mu1 2, that's the discontinuity of mu1 2, is given in terms of the P1, P2 minus P2 tilde P1. So to do that, you just have to solve Hirota equation at this node. You will find this T in terms of P's and mu's, because now we know all of this. It's a simple calculation which I plan to do, but I have just to tell you the result. And then require that the discontinuity is 0, you find that this equation on mu. And now if you proceed in the same way, you will find one by one all these T functions. And then the requirement of, say, analyticity of T to 0 will give you the following statement. So tilde denotes P as the snack sheet, the one you asked about before. So again, the algorithm is the following, and actually there is a simple mathematical code which actually my computer failed to show because I don't know, some Windows problems. But if you compute this T to 0 and require doesn't have cut at plus I over 2, you can actually find a very simple equation on P. So our goal is to fix P, and it gives this discontinuity equation on P. And then if you continue this way and go further up in the stick hook, you will find exactly the same equation, just for different ends. First when equals 1, then when equals 2, and so on. And of course, if you are not stupid, you will decide that this should hold for any n. Right? But actually proving this is a complicated exercise, because this T, they becomes very, very complicated combinations of P's and mu's. But all this math boils down to this single equation. So let me finish here, and let me conclude that all the TBA information stored in TBA reduces to the following parameterization of T's in terms of two nice functions, P1, P2, which has only one cut, and in terms of this periodic function mu1, 2, such that mu1, 2 plus I equals to mu1, 2 of U, with an additional requirement that P1 tilde, then you shift by I. If on another shift there are many cuts, and if you go to this cut, you can re-express the result again in terms of P1 and P1 tilde. So, after the lunch, I will tell you the consequences of this equation, how it can be written in a nice form. And we'll consider some example of calculation where we can actually solve exactly for any value of coupling the TBA equations, which are now very simple. They just reduce to this single equation.